All right. Good evening or good afternoon whenever you're watching this. Our topic this week is traffic volume studies. So this is really one of the fundamental studies that we do with traffic. And of all the chapters that we've done, I would really encourage you on this one to make sure you're reading the book. It's not a real quantitative topic. The math's certainly not hard or anything like that, but there's a lot of terminology and there's a lot of procedural things that go with this. And so reading the textbook will be really helpful. So we're going to look at the difference between demand and capacity, look at why we use the 30th highest hour for design, calculate the impacts of design exceeding capacity, and then we're going to look at various traffic volumes in different situations and how to perform a bunch of different counts. So we're coming back to some terms we've used in previous lectures and previous weeks, but we have traffic volume, we have the rate of flow, demand, and capacity. So look up those definitions in the textbook, but we're also going to use them in the samples as we go through here. So this is a really important concept. The top graph shows the capacity of the road. In this case, it's around 6,100 vehicles per hour for the flow rate. But there's a greater demand from hour 1 to hour 2, basically. And so what you see on the bottom is what actually happens with the flow, right? The flow cannot exceed the capacity. So even when there's more demand than there is capacity, we can't service that. So what ends up happening is the flow gets capped at the capacity, and then it carries over, and we have this kind of leftover demand that gets served later. So this is queuing. So if you think of like being at a Cardinals game, the roads can handle all the traffic, maybe before the game when people are arriving at different times, but after the game and everyone's leaving at once, the demand exceeds capacity, and we have this long queuing on various roadways. And that's really what we're talking about here. And this is a good example. So on approach 1 and approach 2, in approach 1, the capacity here is 4,000 vehicles an hour. The demand is 3,800. And so all 3,800 cars can get through, right? Because the demand is less than the capacity. Same on approach 2. The demand's only 3,600. The capacity is 4,000. So all those cars can get through those approaches. But what happens when they combine, when they merge into this 3-lane section immediately downstream? Now there's a combined demand of 7,400 cars that want to get through here in an hour, but there's only a 6,000 capacity. There's only 3 lanes here to serve them. So what would happen in this instance is the traffic would back up from the merge point, as you can see those squiggly lines, and it would back up onto the approaches. So even though the approaches each have enough capacity, their combined demand downstream, there's not enough capacity to serve it, and that creates a bottleneck. So kind of rule of thumb, numbers that we use a lot, day-to-day practice. A 2-lane highway has about 1,700 passenger car equivalents per hour in capacity. So basically what that means, if all the cars were passenger cars, of course there are trucks, and so trucks would count as a factor. They might count as 1.5 cars, right? But we talk about passenger car equivalents. And for a 2-lane highway, it's about 1,700 per hour per lane. And when you get to a multi-lane highway, that goes up. So we've got 1,900 to 2,100. And the reason that there's higher capacity on a multi-lane highway is because it's easier to pass. And also it's typically easier going faster. So it's designed as a higher free flow speed. And in freeways, where you have even less friction, right? You don't have really any at-grade access. You can get up all the way to 2,400 cars per hour per lane if it's a high-speed facility. So there's just some rule of thumbs for capacity to have in your mind. So traffic varies a lot, and it varies by year, it varies by month, it varies within each week, it varies within each day, and it even varies within each peak hour. So as we're looking at these, we're gonna kind of break each of these down and talk about how they impact our volume studies. So from a yearly standpoint, we would typically say that growth is almost, or the year-to-year ADTs are almost always going to go up, right? That's not entirely true. It used to kind of always be true, but then when we have big recessions, so like in 2008 when the economy goes down, we actually saw a decrease in travel. So on some key roadways, the ADTs actually went down for a while, and now they're going back up. But in general, when you look at a long period of time, you're going to have positive variations year to year as traffic grows. You could also have a spike if there's a significant generator. So if a road has a big development next to it, obviously that could cause a significant increase. But we typically talk in terms of annual growth rates. And so this is just like a exponential growth equation. So to find the ADT in the future, we would take the current ADT and multiply it times 1 point whatever the growth rate is with an exponent to the number of years. So for instance, if we had a 2% annual growth rate and it was a 20-year projection and the ADT was 10,000, it would be like 10,000 times 1.02 to the 20th power. And that's how you get the future growth. So it's exponential. So it compounds over, it's compounding growth. So keep that in mind when you're looking at yearly. So monthly, this varies a lot depending where you are in the year, but you can think of the things that influence this being weather and holidays primarily, and school schedules. So you can a lot of places the summer will be more than average travel. People out of school, they're vacationing. If it's a recreational area, that would certainly be true, where you get a lot of visitors. And then typically, January, December, especially if it's bad weather, or that'll be down. But that's also down because of holidays. People are not on their regular commutes as often. People are sick more often. Those kind of things. Typically, if you could pick any month to count, you typically want to look at like May or like October, November. Those tend to be nice, steady months before the weather and school really impacts them too much. So what happens is we almost never can count in the month we want to. If you have something that's very critical, like if you're counting for a school, you pretty much have to count outside the summer. It would make no sense to count in the summer for a school or adjacent to a school. But other than that, you can kind of count any time of the year, and then you just make adjustments based on historical month-to-month comparisons. So if you counted in April and it was lower than the average month, you would just bump it up by an adjustment factor to make it an average month. And then within a week, you can imagine the day-to-day changes a lot. Weekends are much different than weekdays, and depending on the facility, weekends could be higher or lower. If it's a commuter facility for jobs, it's going to be higher in a week. If it's a recreational facility, it could be higher on the weekends. So typically we're looking at midweek. So we typically try to focus our counts on Tuesday, Wednesday, and Thursday. Mondays and Fridays aren't as reliable because people are more likely to take days off on those days, either sick or vacation. People come in later on Mondays and leave earlier on Fridays sometimes. So we tend to stick with Tuesday, Wednesday, Thursday for our weekday counts. So if you look at some profiles here, for an urban setting, we would usually see a peak in the morning, 7 to 8, something like that. And then in the evening, the peak is usually spread out more and more intense. Basically, there's more variation in morning work schedules, whereas in PM, a lot of people get off at the same time. The other thing that happens in the PM is you have a convergence of commuter traffic with shopping traffic, right? People are out eating and they're out shopping at the same time people are getting off work. Whereas in the morning, there's a lot less of that. And in a rural setting, it depends a lot on where the rural setting is. A recreational site, like in the bottom or the middle there, you can see like on a Saturday, Sunday, it might actually be heaviest, and it's probably going to be heaviest in the afternoon when there's a lot of recreational activity. But, for a local route, it looks a lot like an urban, like the one on the bottom. There's a morning and afternoon peak. So, they for rural areas, it depends a lot on who's using those facilities. But there's also variations in urban settings. If you could look at all of these being an urban setting in a weekday, and the profiles are a lot different, right? So the top one, I would guess, has a lot of commercial activity along the corridor. So there's a lot of shopping in the afternoon. The bottom one, or the second one down, probably has maybe a factory use or a school. So there's a big spike in the morning, then it kind of evens out throughout the day. The third one down is pretty steady all day, so it's probably a mixed use corridor and you can see it stays up in the evening, so there might be like entertainment district nearby. And then the bottom one is very similar to the second one. But so in general, we're going back to this. This is pretty typical urban, but it can definitely vary. It just depends on what the corridor is used for. So we've talked about yearly, monthly, and weekly. So now, and really hourly within a day, right? That's what these profiles are showing, that throughout a day, by hour, they change. Well, even within an hour, things change, right? And so we talked in one of our previous classes about the peak hour factor and how even we'll identify the peak hour for our capacity analysis, but within that, what we're really focused on is the peak 15 minutes. So we'll look at the peak 15 minutes for our design. And so we look at the whole peak hour and then we calculate the peak hour factor. And what that really tells us is how peaky is it within the hour. So if you have a school that's got a really condensed arrival time, you may have a very high peak hour, or in that case, low peak hour factor, meaning there's a big peaking. And so it's not a steady 15-minute periods. One's much higher than the others. Whereas if you're in a more commuter corridor and there's no like event that would cause a real big peak within the hour, you might be much closer to 1 as a peak hour factor, which would mean all 4 are very even. And so we look at those 15-minute peaking factors within each hour. So we've mentioned in a previous class about the 30th highest hour, and we kind of talked about how this was used for design. We didn't really talk a lot about it, but I think that this exhibit will kind of give you a picture of that. Why 30th? Well, if you look at all the various roadway types, we got recreation here at the top and urban down towards the bottom. If we instead used the 100th highest hour, meaning it was the 100 of all the hours in the year, only 100 are heavier than that, you can see we're still missing a lot of traffic, a lot of volume because of the shape of the curves. But if we go back to the 30th, we capture almost all the demand. So in other words, if we chose something like 100th, we would have a lot of times and a lot of volume that would exceed that, and we'd have some significant capacity constraints a lot of the time. Whereas if you get to the 30th, even when it exceeds it, with the exception of the top rule one, even when it exceeds our design, we still are not getting a lot of demand past that. And so it just has to do with the shape of these curves and how the heaviest hours are really heavy, but even 30th, for the whole year to the right starts to flatten out a lot. So that's why we use the 30th. It just captures almost all the demand without extraneous cost. So that's kind of traffic volumes 101, an overview of how volumes vary. And so now we're going to talk more about actually how you perform the studies and how you collect the data. So how much data do you need? Typically in a more urban setting, it's going to be less seasonal because people drive to work and go to school and stuff regardless, other than the summer, obviously for school. So you need less data. So typically if you had daily counts for even 8 months of the year, you can pretty much predict the rest of the year. Rural can be a lot more seasonal. It can be a lot more impacted by weather. It can be impacted by recreational activities. So you're usually looking for, a more robust data set because rural is just less consistent. So these look a little bit complicated. Again, just look through your book. These are really simple. The top's just a daily factor, and the middle is the monthly factor, and then the bottom's the ADT. And basically the ADT is the volume that you actually count on a given day times a daily factor saying it's Tuesday and a monthly factor saying it's November, right? We're going to go through an example here. So in this case, we go out, we do a traffic count. It's a Tuesday in September, and we counted 9899 cars that day. So we had a tube out there across the road, and there was 9,899 cars that day. But what we want to talk about is in terms of ADT. So if this was an average day throughout the year, is that accurate, or should it be higher or lower? So that's where these factors come in. And so the factors are going to vary by road and by region. So they're usually published by the state DOT. But if you look in your book, there's a table 9.11, and it's got some factors for a given facility. So if we assume that those apply, and like for an exam or for the homework, you'll be given the assumptions. You'll be given a table with these factors. But because we're on a Tuesday, it gives us a factor of 1.121, and because we're in September, it gives us 0.884 as a factor. So to get the actual estimated ADT, you simply multiply what you counted times those two factors. So 9899 times the 1.121 times 0.884. So in this case, our annual ADT is slightly less than what we counted that day. So a Tuesday in September would typically have a little higher traffic than an average weekday any other time of the year. So that's the solution for how you do those adjustments. This would have been an in-class exercise, but obviously we're not in class. But I'd really like you to do this on your own. It's a great practice, and a lot of it's review over some of the things we had before the last exam. So the next slide, I will give you the solutions, but I'd really like you to work through it and then check back on the solution and make sure you get the same. So we're saying here there's a traffic count. It was done on a Wednesday in January. There's a bunch of data on the next slide. We want to know the K factor, the D factor, the ADT, and what direction we think the city is, just based on the patterns that you see, and estimate the minimum number of lanes. Right, and go back to those rules of thumb about 17 to 2,400 vehicles per hour per lane capacity. So these are our counts hourly, and so you can pause this, look at those, and try to come up with those calculations, and hopefully you get something close to this as your solution. So that's kind of general traffic volumes and how we collect them and how we adjust them. So now we're going to talk about some specific applications of different types of counts and when they apply. So the first one we're going to talk about is intersection counts. And these are 90% of what we do in practice, because we're usually trying to design an intersection or look at the traffic control or see the number of lanes, see the pedestrians. And so we're typically counting at an intersection. And so as the slide indicates, to do this manually or by hand can be, pretty complicated if it's a busy facility, if there's a lot of lanes, if there's right turn lanes, people kind of sneak by the right turn lanes on red, so it's hard to see everything. So rule of thumb, you need usually 2 people to count an intersection. You just split up the legs. If it's a really big intersection or if it's something complicated like a roundabout, you might need, multiple people. Now, this is how you're going to do your term projects, because none of you are going to have access to what we use in practice today, which are video counts. What we would do most of the time today, we still do this sometimes. If it's a small project, we want something quick, we'll just send someone out and they'll sit there and do the counts. But we usually hire a third party. They come put cameras in, and then those cameras run through a software, and there's an algorithm that can identify the vehicle type, the turning path, all those things, and give us a really accurate count without having someone sit out here and actually record these. But in my early days of my career, I spent many, many, many hours sitting out there counting, because I was the low salary on the totem pole, and it made most sense for me to do that. There's a lot of value in that, because you start to understand what 100 left turns an hour looks like. You start to get a real feel for traffic operations, but really it's just not efficient to have someone sit out there now that we have other options with technology. So when you're sitting at an intersection or even looking at a video feed, you can imagine there's cars coming to the intersection and there's cars leaving the intersection. So and oftentimes there's a difference in the two, right? Because we're counting in 15-minute increments. So if a car pulls up, in increment 1, but then it flips over, and now before it leaves it's in increment 2, how do you account for that car? And what we want is what we want is arrivals, because arrivals tell us the true demand. If there's a bunch of queuing at the intersection, the amount of cars getting through it could be constrained by the capacity of the intersection. We want to know what's the demand, so we actually want to know the arrivals. But we can't actually count arrivals directly very easily, because any car sitting in the back of a queue, you don't know if it's going to go left through or right. So what actually happens is we count departures, because we can actually see this car went from a northbound and then made a left, right? So we can record that. And then we account for the difference between arrivals and departures by measuring the queues at a given time, which varies, which we're going to show in the next 2 slides. But so the queue is just basically the leftover cars that couldn't get through because the capacity was not adequate. So at a signalized intersection, we're going to record the departing cars. Then we're going to record the queue at the beginning of each red phase, as the signal runs through. Now, again, in reality, we very rarely do this. A lot of times the intersections are not over capacity, or we say, this is close enough. But in a technical sense, this is what we're expected to do. At stop controlled, it's very similar, but we don't have red phases. So instead, we just, at the end of every 15 minutes, we measure the queue. And so, again, a bunch of terms here, but really all we're saying is to get to the arrival volume, which is what we want, we just have the departure volume plus the queuing that's there minus the queue from the previous period, because any queue that was there in the previous period got through the intersection as part of your departure volume, right? So you don't want to double count it, and we'll go through an example here. So this is a very typical example. So from 4 to 4:15, 50 cars arrived. There was no queue. So our arrival and our departure are the same, right? No one got left behind. But if you look at like 4:30 to 4:45, 62 came, but only 57 got through. So we had 5 sitting there in the queue. So at the next 15-minute period, we counted 65 arriving or departing rather. Sorry, and but then we had 10 left over in the queue, and so on. So how do we get to the arrivals that we want after we've counted only departures? It looks like this. So if we look at 4:30 here, you'll see 62 plus 5 is 67. It's real simple. There's 62 there. There's 5 left over, so the actual arrivals were 67. But if you look at the next line, we have 65 plus 10 minus 5. So that's the 445. 65 plus 10 minus 5. And what's going on here is you have the 65 plus the 10 on that line. Makes total sense, right? We counted 65 leaving and there's 10 left over. But we have to remember that the 65 included 5 from the previous, right? So we don't want to double count those 5. So that's why we get 65 plus 10, then we subtract the previous 5. And you just go on down the line. So there's several periods here, 15-minute periods that are impacted by queuing. So that's how we get from departures, which we can actually count, back to arrivals, which is what we actually want to use. So we're going to talk now about some of at the end I'm going to talk about how to actually conduct a full intersection count if you're managing a crew. But for now, the basics here are, if you're going to go study an intersection, you need to visit it. You need to understand what you're studying it for, what the area is like. Do you need to count heavy vehicles separately? Do you need to count buses separately? Are there going to be a lot of pedestrians that you need to be aware of? Are there a lot of cyclists you need to be aware of? Because you want to, either you or whoever you're sending out to count, they need to be aware, hey, on this one, make sure you count, dump trucks because it's next to a dump, right? Or heavy trucks because it's next to an industrial plant, those sort of things. And as we're going to talk about when you're scheduling these, people need breaks. This is monotonous work. And so it's nice to have a floater that can go around and relieve people for 15 minutes. So they can go get a drink or use the restroom, that sort of thing. So when you go count at an intersection, it's going to look something like this a lot of times. And so this is kind of one snapshot that tells you everything. In this case, it's 12 hours of data. So you can see up there it says 12-hour count, 7 to 7 on a Tuesday in 1964. But if you say, let's say, as an example, on Blossom, which is the bottom, so we talk in terms of northbound. So on the right part of the bottom leg, you'll see a 7355. So that's all the arriving traffic northbound. So there's 7,355 cars in that 12-hour period that are coming northbound. Of that, 6508 go through to the north, 646 go left to the west, and 201 go east and turn right. So that's the 7355. But if you look at Main Street in the bottom right, that's 6562. Those are the arrivals, right? So those are that's the sum of the southbound lefts, eastbound throughs, and northbound rights. So if you look at this a little while, it'll become clear. But there's a lot of data here all kind of captured in an intersection flow diagram. So that was intersection counts. That's by far the most complicated. Another type of count we might do is a cordon count. And you can think of this as basically if you drew a circle around your area of interest, what are all the ways or all the major ways in and out? So if we looked at SIU's campus, right, there's only 6 ways to get in or on or off campus. And so if we counted those intersections or we put hoses across those roadways, we could measure the total flow in and out every 15 minutes to an hour, depending on what the purpose of our study was. So when you do a cordon count, it's important to fully enclose the area of interest so you can count everything. The counts directly apply to parking accumulation. So this is one of the big applications. So if we wanted to say, how many people, what's our peak accumulation of parking on SIU East campus, right? Rather than going out and counting all the people in the parking spots, which is a lot harder, if we counted all the ins and all the outs every 15 minutes from morning to night, we could say, here's all the ins, for that hour minus all the outs. Here's all the ins the next hour minus the outs. And you can keep a running total, and you can get a peak accumulation. So you'll know that, say, at 3 p.m. or whatever the peak is, there's a total of 8,200 cars on campus, and then it starts to decrease again. So that gives us a lot of insight about the demands within, in this case, SIU East campus, or this is Vancouver. If you have an island, this is pretty easy because you only just count the bridges. But you're basically trying to minimize the count you need and gather some global information about an area. So if we were looking at Springfield, Illinois, for example, and we wanted similar data, I would probably count on Interstate 72 to the west, Veterans Parkway to the south, 55 to the south, say Route 29 to the east, 72 to the east, 54 to the east, 55 to the north, Route 4 to the north, and David Jones Parkway to the north, and then 97 to the west. Basically all I did was draw a circle around the city and looked at the major crossings. There's some minor ones in there that aren't really that relevant, but if you count the major ones in and out, that's really what we're talking about with a cordon line count. And, plotting that data will look something like this. And again, it directly correlates to parking demands. So screen line counts are in some ways similar, but here we're looking at usually a regional flow. So for East-West Gateway, our local MPO, they definitely do a lot of screen line counts, and they've got the convenience of the Mississippi River. So basically, if you count all the bridges, you can easily know the demand between the two states. So that's what a screen line is. It's more of a vertical or horizontal line that gives you the ins and outs across that line. So we have the river. That's a popular way to do these. Something like a railroad, a mountain range, anything that's got you can only get across it in a limited number of ways is a good place for a screen line count. And then we have pedestrian studies. So we'll typically count pedestrians as part of our intersection studies, but sometimes we're looking specifically at pedestrian issues. So we might look at crosswalk compliance. So we've done some studies on WashU Medical Campus, like Barnes Hospital. There's a ton of pedestrian activity, and it conflicts with a lot of cars. And so what we've observed there is there's a ton of jaywalking, right? And it's really dangerous, and people get hit a lot of times outside of crosswalks because people aren't expecting them there. So you can look at like compliance issues. Are people using crosswalks? Are people jaywalking? So you could come up with some countermeasures. But also conflict analysis is really helpful. So what a conflict analysis is, that no one actually got hit, hopefully, while you're out there, but you can see near misses and you can see avoidance maneuvers. So if you sit there and you watch a crosswalk and you see someone that turns right out of a parking garage and they have to slam on the brakes to the point that their car rocks back, we would record that as a conflict, right? Or if someone stepped off a curb and then had to jump back on the curb because they almost got, they thought they were going to get hit, that'd be a conflict. So you can do conflict analysis for cars too, but a lot of times pedestrians are it's a more nuanced situation. And so doing a conflict analysis can be super helpful. So the final thing we're going to talk through here are a few count parameters, and then how to do an actual count as a consultant. So something that comes up a lot is if we have a study area with multiple intersections, what we'd love to do is have, counts for every 15 minutes for a whole year at every intersection. That never happens because no one can pay for that, and we don't have the time to spend on it because we need to have the findings sooner than that. So we're typically going to count for just the peak periods, right? And we're typically going to only be able to count maybe during 1 week, maybe over 2 weeks. But even then, we're not going to count every location every day for 2 weeks because it's just not necessary and not efficient. So what do we do? So in this example, we'd like to have 8-hour volumes everywhere. We've got 7 different intersections. And so what we would do is we would choose one location that seems like it would be the most representative of the area. We will do the full count there, and we'll call that a control count. And then we can do coverage counts at the other locations. So in this case, we could count location 7 for the whole 8 hours, but location 1 to 6, we'd only count for an hour each. And we could count those at different times of the day. We just have to be really careful that we document and know exactly when we're counting. And then if we have some regional factors, from the DOT or the MPO, we'd still adjust all these for seasonal factors. But as far as this small area, we can reference count 5 or count 6 back to count 7 and be able to make some really good estimates that, well, I counted this one at this time and this one at that time, but count 7 ties it all together because it's a control location and we have the data for all 8 hours there. So yeah, so kind of like I said, so scenario 1, if we wanted, we could count all locations for 4 hours, or if we didn't need it, we can count, or if we needed a whole day, we can count all of them for the whole day. But yeah, the point being that 7 remains a control count, and then how much we count the other locations kind of depends on their importance. And so a lot of times some of these will be like very minor, so we might only count them for an hour, and then we can tie them back to location 7. And then, if there may be two locations that are pretty important, so we might count those for 4 hours, but location 7 might be the only one that we count the entire time. So the last calculation really with volume studies is VMT, or vehicle miles traveled. It's pretty simple, but basically you're trying to find the volume along a given corridor. So you look at different segments of the corridor, and so for, say, an interstate, you might look between interchanges, right? Or if a highway, if the number of lanes changes, you definitely have to cut that and make that a unique segment every time the lanes change. And then you basically measure the volume in each of those distances, or each of those segments, the length of those segments, and you add it all together. So very easy to see in an example. So this is a given road. Say these are chunks of highway between interchanges. So we've got 10,800 for the first 1.2 miles. Then we've got an ADT that drops down to 8160 for the next 1.4 miles, then back up, then back down. So you see these distances and these volumes, and really all you do is you would take like the 10,800 times 1.2, and that will give you vehicles per mile traveled for that little segment. And then you add 8160 times 1.4, etc. So you just multiply it for each small segment and then add them all together. So in sloppy writing, that looks like this. So the 1.2 times 10,800, 1.4 times 8160, etc. And what we're typically going to sum that up in is for this entire corridor, in this case, 2.6, 3.7, about 5 miles, 4.9 miles. We would talk about it in terms of having a VMT, or a vehicle miles traveled, of 50,280. So something you may be asked to do as a consultant, whether you're at a DOT, or as an engineer, whether you're at a DOT or a consultant, and something I did a lot earlier in my career was manage these volume studies. And just going to give you some quick tips here and kind of how this actually works in practice. So there's some preliminary work. You obviously need to decide what count locations are important. You want to go out and do a site visit to see if you're doing this with people, how many people are needed per intersection, where can they sit? They're going to be able to sit in a vehicle or out in a lawn chair, that sort of thing. You may have to hire temporary workers if there's a big count to do. And then you typically are going to set up a hose count and maybe in multiple locations ahead of time if you can, to identify the peak periods, but at least throughout your count. So you, again, have that kind of consistent central data to go back to and say, hey, Joe counted over here at this intersection. It seems really low. You can check an adjacent hose count and say, yeah, it was low. He fell asleep, or no, it looks about with the hose count, so I guess it's right. It can give you some verification. So we can go out and count with various devices. Like I said, a lot of times now we'll hire video camera crew to go do this. It's their whole job. They do it as a third-party service. But like with your class projects, it can be as simple as a little clicker. Like the one in the kind of middle there is a pitch count clicker. So if you ever play baseball, if you're ever an umpire, you can actually just click it and it just keeps counting. So that's a really cheap way to get this. The one on the top left is like an old kind of 4-button clicker, so you could count like the traffic per approach on something like that. But most of the time what we use, if we're not using a video camera, is those count boards, right? And they can do a lot of different types of studies, but you can see there's basically all the different arrows for the different movements, left, right, and through, and then the ones without the arrows are pedestrians. And it'll just automatically save this data every 15 minutes, and then you sync it into a computer and it makes reports. So those are the intersection counts. And at the bottom row are what you do for ADT counts. So there's the hoses, which is still the most common way that a lot of places count. They go over these tubes that pumps air into the box, so it knows how many axles went over it, and then it can count that. And then VMIs or High Stars, or there's different name brands, but like that silver on the bottom right is basically a device. You might see these on the road when they're covered, usually in a black rubber square. But underneath that, it's a little slightly bigger than a credit card size metal thing. And it's magnetic, so it's counting axles going over it as well, and it stores that data internally. You sync it to a computer, so it's kind of like a host count, but the big benefit of that is you can get it per lane, and it's also much more accurate as far as the vehicle types, because it can pick up the axles better than the hoses can. So you need to plan out what days and hours and weeks you're going to count. Especially if you're going to bolt something into the pavement, you probably need to tell the owner of that pavement that you're going to be out there. And some communities also want you to have a permit, or at least to check in with the local police, so they know why people are sitting around in sunglasses at intersections. So that's just a smart thing to do. It's really important, if you're going to do this, to set up some forms that are very consistent, so that every person that needs to count, their form tells them exactly when to be there, where to be, landmarks that are nearby, where they can sit, where the north is. And so for your class projects, I would definitely suggest doing this, right? So if you're going to go out and count an intersection, you're splitting it up among 4 or 5 of you, make sheets that are very specific to each person. It makes it much easier to not mess up. So for someone to come count, if you're hiring some temporary workers, they don't have to be really excellent in any way. I mean, basically basic math. Obviously, they need to be able to get there with a driver's license. It's great if they know the local area. Just tell them to bring a watch, something to sit on, something to deal with weather if they're going to have to sit outside their vehicle. Make sure that there's gas in their car, so they don't, and make sure they keep their car running at times so they don't kill their battery, that kind of thing. But yeah, if you need to hire some temps, usually DOTs can give some recommendations. A lot of consultants already have favorite temp agencies or college students that they might use. Yeah, I guess those are good. College students are the best counters, especially if they're traffic engineering students, because it's great experience, and we still like to pay those students. They can keep that money, or it could be like an ITE fundraiser as an example. So what you want to do is meet the counters at least half an hour before you're scheduled to start. You're going to go over which way is north, and that's actually really important, because the boards get oriented, or even the clickers. Everything you do, you need to know what direction is north. So make that consistent for everyone. So if the north is kind of like actually northeast, don't tell them that. Just say north is this road, this direction. Look at that. That's north. So everyone's the same. It's great if you have some equipment. You just sit there and practice for 10 minutes, see if anyone has any questions. Let them know that this is not an exact science and that the counts are cumulative, right? So that they can't skip periods of time, but if they think they missed one car, don't freak out and stop counting. Just keep counting. It's not that big a deal. And they should obviously document the counts if they're not being stored in the count board. Get their phone numbers. Give them your phone number so you guys can communicate. And then have a time where you guys meet back and you collect all the data. So once you have the data from the boards, you're just going to make a map of the peak hour volumes, and then you can compare from intersection to intersection if the counts balance. So as all the traffic from this intersection, it's leaving the intersection headed east, is the amount of traffic arriving at the next intersection to the east pretty close to that. And if it's not, there could be good reasons if there's major access in between, but unless there's a big hole in the ground, they should pretty much balance, right? So that's a good way to kind of smell test your data and make sure everything's working well. You can make adjustments if needed, but don't make use wise judgment with that. And if they don't match, really scrutinize it. A lot of times it's because they still didn't get north right? So if the data works whenever you would rotate it 90 degrees, that's probably the case. And worst case, if something just didn't work, the counter died, you had a really bad employee that didn't do a good job, or they left in the middle of the count, which can happen. You may have to go out and recount it. So hopefully your schedule allows you to go make that happen if needed. So this is a screenshot from Syncro, but basically this is what the data looks like in its final form. So let's say this is the morning peak hour. C Street and Valley Boulevard, you can see there's 300 westbound lefts, 375 westbound throughs, 50 rights. And then if we click down into that data, you'd be able to see the percent of trucks, if there's pedestrians, etc. But this is really where where all this effort kind of comes to fruition, is we can use this for our analysis. So that is your remote lecture for the week. Like I mentioned last week, we're going to have 2 assignments, both due here on October 9th. So the one from last week, which was the statistics from the handout, and then we've got some Chapter 9 problems here from the book. So problem 1 through 3, and then 5 and 6. So please turn that in next week along with the statistics homework. Make sure you read Chapter 10. Chapter 10, next week, we're going to be getting into just some other types of studies that aren't just volume studies. So let me know if you have any questions in the meantime. Otherwise, I will see you on October 9th.